Okay, hi everyone. So today we'll be continuing our second lecture. I will be focusing on the detector. Okay, all right. So I'm going to share my screen. Right. So as I mentioned before, there are two. There are a lot of detector for GC, but um, the main GC detector is going to be FID and then and also ECD, electron capture detector. This is going to be the most frequent use of GC detector. There is also another detector which is mass spectrometry detector, but for that kind of detector you will be going into depth in I think in spectroscopy punya subject. Okay, for this GC we are going to focus on GCFID, flame ionization detector, and also GCECD, which is electron capture detector. All right, so for flame ionization detector, as you can see for its name, it is using flame. Okay, it is using flame. So basically, we need to produce flame for in the detector for it to be able to detect all of your analytes that have been separated inside the column. Okay, so using amplified current generated by electrons and organic cations from combustion of organic compounds, this current provides a useful analytical signal. Okay, you can imagine that when your samples and or your analytes is coming out from the end of your column, it will be going into the detector. Okay, so this is the end of the column. So it will be going to the end of the detector, and then it will go into end of the column. It will go into the detector, where the detector is going to be fed with hydrogen gas and also air. So that's why I said in the beginning of it, when I mentioned carrier gas, there is also some carrier gas, hydrogen, and then air. Okay, hydrogen and air is going to feed the detector for it to be able to produce flame. Okay, so for the first one here, you can see that at the end of the column, so all of your analytes coming out from this end of the column, go into the detector and is going to be combust in the flame that is being produced. Okay, so pembakaran akan berlaku di dalam flame ini, yang mana pembakaran analyte itu akan generatekan elektron dan juga organic cation daripada pembakaran itu, yang mana pembakaran itu akan providekan a useful analytical signal. Setiap pembakaran dia akan mengeluarkan electrons. Setiap pembakaran of the organic cation di dalam sampel kita itu atau analyte kita itu akan mengeluarkan elektron, di mana all of these electron would be fed to the collector cathode, yang mana dia akan kira berapa banyak elektron keluar, how much is the electron, how intense is the electron, and all of these are going to be collected by the cathode, where it will at the end akan keluar chromatogram lah. That's what it meant by flame ionization detector, where in the flames there are combustion happens to your analytes, where the product of combustion is electrons, and the electrons will be collected by the cathode, and then it will produce a signal. Okay, so for example, C2 is having a much lower boiling point as compared to C8. So C2 punya combustion and electron generated is going to be less than C8 punya combustion. Okay, so that's how we differentiate on the number of electrons generated from the combustion. Okay. Most carbon atoms except those in carbonate and carboxylic groups, generated a signal which makes the FID an almost universal detector for organic compounds. Okay, as I said before, the most universal one is the thermal TCD, thermal capture detector, if I'm not mistaken. So the thermal is just sensing the thermal that is being produced, the temperature that is being produced by the compound. But the FID, I think that it is one of the most effective and efficient in terms of analyzing or capturing the electrons specifically towards each analyte lah. So it is much more specific, tetapi juga dia universal because it is using flame where most of organic compounds semua combust kan, dia boleh terbakar. Most inorganic compounds and many gases such as H2O and CO2 are not detected, which makes the FID detector a useful detector for the analysis of atmospheric and aqueous environmental samples. So this is the orang kata apa, the specific type of whenever that you are using FID, you need to know that most inorganic compound would not be able to be detected by FID because it's not combustible. And most of H2O and CO2 also would not be detected. So it is useful for this detector to be used in analysis of atmospheric samples and also environmental samples. So that's how or that's why you need to know your samples first, your analytes, apa yang kita nak kaji. Kita nak kaji sampel, environmental sample. Okay, when you know what samples are you going to analyze, you will know what set of temperature, you know what type of column, you know what are the oven temperature, you know what is the detector that is going to be used. So, bila you setiap parts ni, bila you tahu apa keperluannya kepada you punya samples, so it's going to generate very good results. Okay, so that is how, or that is why we create this kind of course for you to be able to differentiate. Okay, I have this sample and I want to choose this as the injector, the temperature, this as the column, why I have my reasons, and this is the detector, I have my reasons as well. So it is not just okay, saya terima saja apa yang ada. Yes, you need to terima lah because itu sahaja yang ada di universiti, tetapi you need to also can think on why you are using that instrument or you are using that part. Okay, so that's what we the objective of this course lah, apa yang kita harapkan output dia. Right. So the detection limit approximately 2 to 3 orders of magnitude smaller than that for thermal conductivity detector. Okay, the detection limit is quite it is much more smaller than 2 to 3 orders of magnitude lah, maksudnya for thermal conductivity detector, thermal conductivity detector, you would achieve much more higher order of magnitude. Tetapi as I mentioned, for FID, if you have environmental samples, atmospheric samples, or any organic samples, when you use FID, the detection limit is much more smaller, but it is much more specific towards your analytes. Okay, the sample is destroyed when using a flame ionization detector. So when I say destroyed, so it means that at the end you cannot collect back your analyte because it is destroyed inside the flame. So basically we can say that for flame ionization detector, your analytes is destroyed. You cannot collect back. Okay, so that is flame ionization detector. Okay, yeah. So this is the the flow chart of it. A flame is produced by burning hydrogen in the presence of oxygen, yes. A portion of eluate coming out from the column is directed into the furnace through the wire loop. That's what I explained earlier. At the end of the column, so towards the end of the column, your analyte will come out and go into the flame, and then it's going to be evaporated. The solvent is going to be evaporated, and also the organic compounds are going to pyrolysis. Pyrolysis means it is going to be combust and form ions. These ions are attracted towards respective electrodes. This changes the potential difference between the electrodes and hence the current in the circuit. So this explanation is much more detailed of whatever that I explained earlier. But basically, the flow is like that. Whenever you are going to explain how FID, how flame ionization detector works, these are the flow, okay, on how it is used, on how it is functioned, okay. As electrical resistance of the flame is high and resulting current is small, an electrometer is employed, which generates your chromatograph. Okay, so that is FID. And then ECD, it is an electron capture detector. Now we also going to play around with electron, but for ECD, it is a selective detector. All right, so it is a selective detector. Okay, selective detector means that it only detects a small amount of sample. It's very selective. Small group amount of sample, not small amount, sorry. It is small group of sample. It is not as universal as FID or as universal as TCD. Okay. The detector consists of beta emitter, electron emitters such as nickel 63. So the detector consists of beta emitter. The emitted electron ionized the mobile phase, which is usually nitrogen, generated a standing current between the pair of electrodes. A solid with a high affinity for capturing electrons, elute, decreases the current, serves as the signal. So in this case, the carrier gas is going to be ionized, usually nitrogen. So a solute with a high affinity for capturing the electrons would decreases the current, which serves as the signal. So in this case, we are going to play around with the mobile phase. So mobile phase plays a role in the ECD where nitrogen, okay, you can see that the carrier gas in here, so the carrier gas nitrogen. So nitrogen itu akan diionizkan oleh this beta emitter, yang mana dia akan createkan a standing current between cathode dengan anode ini. Okay, bila dia telah diionizkan, elektron ada di sini. Kalau sampel you masuk and sampel you capture some of the electrons here, which decreases the amount of electrons here. So dia kan tadi contohnya bila dia ionizes, you have 100% of electrons here. But when your samples, when you analyze, flow into the detector, it captures some of the electrons, which reduces the amount of the electrons. This decreases in the electrons would act as a signal. So that's how ECD works. Okay, that's why we say the electron capture. So your analytes will capture the electron that has been generated inside your detector by beta emitter and your mobile phase, which is in this case nitrogen. Okay. Highly selective towards solids with electronegative functional groups such as halogens and nitro groups. So this, what I meant when I say earlier that ECD is a selective detector. It only applies to certain analytes, which is in this case halogens and nitro groups, because of the presence of electronegative functional groups. The presence of these functional groups will attract the electron, will capture the electrons that is present freely inside the detector. Relatively insensitive to amines, alcohols, and hydrocarbons. Because in this, for these compounds, or for these functional groups, there are no electronegative atoms, which cannot capture the electrons. The detection limit is excellent, but its linear range extends over only about 2 orders of magnitude. So now what we are hoping is that you would be able to differentiate between these two, FID, ECD, and what are the samples that can be analyzed? What are the analytes that can be used using this detector? And how does this detector works? It is as simple as on how you explain. Macam tu, okay, ECD macam mana ia terjadi? Okay, dengan adanya beta emitter dan dengan adanya nitrogen gas, apa beta emitter itu buat pada nitrogen gas? Beta emitter itu akan ionize nitrogen gas, akan create all of these free electrons. So all of these free electrons will be captured by your analytes, which in this case, halogens and nitro groups. Why? Because halogen and nitro groups have an electronegative functional groups. That's it for ECD. For FID, you would see that FID ni, yang ni lah kita nak explain cara FID tu macam mana it works. Okay? Alright. So that's it's all for ECD and FID. Thank you.